So once we have our parameterized curve, given as a vector function of a parameter, we need to be able to calculate the tangent to the curve, okay? And this is something that you already saw in a past chapter when we did differentiation of vectors, but it's worth seeing it again, okay? So here I'm showing a parametric curve, which is this black curve here. And you can see that vector r, which is the blue vector, points from the origin, which is here, to each point in the line as we change the parameter u. So you can see that the parameter u changes in this direction. So when u equals 0, maybe we are here. When u equals u1, we are here. When u equals u2, we are here. When u equals u3, we are here, and so on, right? And now we're interested on a way of finding this red vector here, which is tangent to the curve. And not only is it tangent to the curve, but it also tells us about how fast the position vector is moving with respect to the parameter u. And the way to calculate this vector tau, this is the Greek letter tau. So this vector tau will also be, of course, a function of u. It is a function of u because as we move u between u1, u2, u3, u4, we also get a different tau. Tau of u1, tau of u2, tau of u3, tau of u4, right? So tau is clearly a function of u, and it's simply given by the derivative of r with respect to u. Remembering that r is a function of u. Okay, so it's simply doing the derivative of r with respect to u. We know that the direction of tau is tangent to the curve. And we know that the norm of tau, given by the norm of tau like this, yeah. So you would calculate the square root of the squares of the components added up, yeah. Tells us about how much r moves per unit increase in the parameter. And the best way to understand this is with an example. And the best example is to consider that our parameterized curve r of u. So let's imagine that u is time. So we are using time as a parameter, right? So then r of u becomes r of time, which is just the position vector of some mass, for example, a fly that is flying around the room. So as time changes, the position vector of that fly is also changing, right? So then if you calculate the derivative of the position with respect to time, you are basically getting a vector which would be the velocity of the fly, right? So that velocity vector is tangent to the path of the fly, and the length of that velocity tells you how fast is the fly moving. In other words, how fast is the position of the fly changing per unit increase in time, yeah, per unit time. So that's just an example in which the parameter is time. But remember that the parameter can be anything. It doesn't have to be time. It can be just some mathematical variable u that doesn't have any physical significance. It's just a parameter that we use to be able to parameterize this curve. Okay? If we go back to our applet in Mathematica, where I could change the parameter t, and this would change the position r. So imagine that this is the position vector of a fly moving around the room. So if I now calculate the derivative of r with respect to t, I get the red arrow, which is indeed the velocity of the fly at each instant in time. So you can see that when I change time, the velocity is also changing, and it's always tangent to the curve. Okay? So I hope that's very clear. See you in the next video.